All right, let's jump over to this first problem, which is the first problem on test of independence here. I can't, I'm not even sure this is a good idea. I can't imagine you're going to like this video very much because I want to run through this particular test by hand all the way out. It's fairly gory when you do that. And if nothing else, that will kind of show you in detail what's going on in this test, and B, maybe make you appreciate what the calculator's doing for you for these tests of independence. So let's go ahead and let's get started here. Test of independence now, as opposed to the goodness of fit test. Goodness of fit is associated with one-way contingency tables, independence two-way contingency tables. There are two variables, a row variable and a column variable. The column variable in this case is handedness, either right or left. Okay, handedness. Okay, and the row variable is height, and I must say I've forgotten what the variable possibilities are. They're short, medium, and tall. Okay, and the observed data is 3, 5, 2 in 1916, 15. 1916, 15. All right, so these tests of independence are very different than other tests. Actually, they're not very different from other tests. They're actually fairly similar to the goodness of fit test. In both cases, you have some observed values, there they are, and you've got some expected values that you might have to calculate, yeah? And I'm going to show you how you do that calculation in this case, because this test of independence is about whether or not this height variable is in any way related to this handedness variable. The null hypothesis is always, I'm just going to say, independent. Meaning there is no dependency between these two terms. And the alternate hypothesis is, of course, it's dependent. So you ought to take your time and write that out and say handedness does not depend on height, or handedness does depend on height. That's what you'd say in this particular case. So what you have to generate is a second two-way contingency table that would have these same properties if there was no dependence, if they were independent. So let me show you how you do that. Let me first total all these up. This is 10 over here. This is 22 down the side. These subtotals are important. These are 21. This is 17. This is 31, 40, 50. So I've got 60 this way, and I should have 43, 60 that way. Okay, so the table itself, don't get confused, the table itself is right in there. But what I want to do now is, in this table, I'm going to just jam this information in here. In this table, I want to write down, how to say this, what these numbers might be if they were independent. And the way you approach this is to say, well, I've got 60 subjects here, some of which are left or right-handed, some of which are short, medium, and tall. They sort of, I did a sample of these 60 people, and this is the way that they fell out. If I wanted to calculate how many people fall in this short right category, I could do that if I somehow knew that probability. If I knew the probability of reaching into this bag of marbles and pulling out a short right person, if I knew that, and if I multiplied that probability by 60, I would get the count I would get the count of the number, in this case, the number of people that are short and right-handed, yeah? So how the heck could I calculate the probability of being short and right-handed? Well, if it's the case that there's no dependence between short and right-handedness, then the probability of being short and right-handed is the probability of being right-handed times the probability of being short. And the probability in this set of being right-handed is 10 of these 60 people, 10 are right-handed out of 60. And the probability of being short out of these 60 people, 22 people are short, are 22 out of 60. Okay, so what I'm going to do now is calculate for each one of these terms what that, the product of those two probabilities times 60 is, all right? And I'm going to put it right over here. So I'm going to call these things that I'm creating e-values, and this particular e-value that I'm going to calculate to put right here is e sub 1, 1, meaning it's the e-value that goes in the first row in the first column, that guy right there. So what we've said is, if I wanted to calculate that, I'm going to multiply 60 times the probability of being short times the probability of being right-handed. So, probability of being short, 22 out of 60. Probability of being right-handed, 10 out of 60. Just like that. Let me go right over here to E2, 1. 1, 2, E1, 2. The E that is in the first row and the second column. That's equal to 60 times the probability of being, in this case, medium tall, 21 out of 60, times the probability of being right-handed, 10 out of 60. E13, I'm looking right here now. E13 is 60 times this probability times this probability, 10 out of 60. Okay, let me just go into hyperspace and finish these off now. I'm going to do second row, first column, and so on. Okay, so it's not easy working that fast. So I've done the calculation for each one of these positions. So this thing that I've written in, if you can see the green here, I've just transposed over this set of O values, the new set of E values. And if you look at them, they compare pretty well. And that's got to give you a hint that the O values are sort of set up in a manner in which they are fairly independent, because they're very close to these green values. And how do we judge whether things are close enough? Again, that's what hypothesis tests are all about. You've got to find a test statistic. You got to see what the p-value of the test statistic is. So here's the last calculation, or the last two calculations. I've got to calculate the test statistic, and it is the same, essentially the same test statistic that we used in the goodness of fit tests. It is chi-squared test is equal to the sum of all of the O minus the corresponding E value squared divided by E. So if I'm going to do that by hand, I've got to do these 6 calculations. Let me go into hyperspace. So there's the chi-squared test value. All right, let me just review what we've done. We were given this pink data, the observed values. We calculated this green overlay, which was the two-way contingency table associated with those observed values. That was independent. We now are doing the chi-squared test statistic to judge how close the pink values are to the green values. And the way we're going to do that is to calculate this test statistic, which in all cases is this value minus this value squared divided by that value. This value minus this value squared divided by that value. add them all up. In this case, we've got 1.21. I now want to calculate the p-value associated with that. That requires that I go to chi-squared CDF. The lower boundary is 1.211. The upper boundary is 10 to the 99th. And the degrees of freedom for these independence tests are the number of row categories, in this case 3, minus 1, 2, hold 2 up over here, times the number of column categories, 2 minus 1, 1, 2 times 1. So it's the number of categories minus 1 along the rows times the number of categories minus 1 along the columns. Those two are multiplied. 2 times 1 is 2. And if we run that, we get 0.546. Trust me, I've done that. So 0.546 is a big number. That means that you failed to reject the null. All right? And if you fail to reject the null, you have to keep the null. That means that this pink data is independent. So I think we can all agree that I have probably made the most gruesome, hopefully the worst video that I'm going to make. I tell you, when I'm bored myself, I got to imagine you are as well too. So sorry for that. Let's get on board with problem 2, and we'll just take it from the beginning and use the calculator. But now you know what's going on. You can see the sausage being made inside these things. All right, see you soon.